Okay, I guess we can get started. So this is a non-paper session, and we have Vyas Sekar, who's going to be talking about reflections on the research and product design process. Vyas is a Tan family professor in the ECE department of Carnegie Mellon University. He serves as chief scientist of Conviva and a co-founder of Rockfish Data. He has received numerous awards: SIGCOMM' Rising Star Award, SIGCOMM' Test of Time Award, National Security Agency Science of Security Prize, NSF Career Award, and many, many more. I have a lot of respect for Vyas because he's somebody that his work very much impresses me, because he's somebody who has continually made extremely deep contributions to the field across such a broad range of systems and technologies, from internet measurement to content delivery to wireless systems. And so I think he's incredibly qualified to talk about what he's going to talk about today. So yeah, thank you.
Thanks, Matt, for the very, very generous introduction. So when we started these sort of non-paper sessions for the first time, we were like, okay, what's a good non-paper session track? And so one thing I thought, especially for like students in the audience, is students come to say like, oh, how do you pick problems? How do you do research, right? This is like the meta aspect of like research. The output that you see at SIGCOMM is often the years of like multiple years of toils, multiple iterations of many things. It's not like doesn't happen overnight. And it's useful to think about like what is this meta process of research. And the more I've had the good fortune of like seeing stuff working with students at Carnegie Mellon, as well as like sort of like technologists at Conviva and Rockfish, the more I realize that there's a lot of commonality between the research process, the product design process, the problem formulation process, this is sort of like the aha moment for me came about a year ago. Is like, I wish I had known this sooner, right? If only I had known this 20 years ago when I started as a grad student, maybe my life would have been so much more efficient. For the record, I never ever had a first author paper at SIGCOMM as a grad student. So all the students in the room who actually had a first author paper at SIGCOMM, congratulations, you achieved far more than some of us ever achieved as a student. So this is one of those things where I felt that I wish I had known some of this sooner. So by the way, even though this is a talk, please feel free to make it interactive, ask me questions, interrupt me. I might even like call on some of people to give their perspectives on this process. And the reason, I think one of the talks yesterday, I think said something about like all models are wrong, but some models are useful. I think this was Kevin from UMass who actually said this in his talk. The same thing is true for advice. All advice you ever hear is wrong, right? Everybody is extrapolating from a small sample set, which includes themselves. It's a biased sample. So all advice is wrong, but some advice is useful. I hope that this advice is useful. Okay. So always start with the why. Why are we here? This is, to me, the meta aspect of research, which is the intangible part of how do we pick problems to work on? How do we formulate the problem? How do we tackle problems the right way? How can we be more effective in communicating our results to a broad audience? And I'm sure like many people in the room, and including me, I always wish I had known I'm more efficient in my own research. Right? It's like, okay, if I was more efficient, I could be more productive. I wish I had known this sooner. And my students often make fun of me. Is like, you seem to be this repetitive machine that says the same thing over and over again. And that is like, okay, if I'm that repetitive, I should just make it into a slide deck and give it to everybody. If it seems to work sometimes. So so I figured I'll just make a slide deck and talk to people about it. All right. So because I'm a professor, I actually like to give homework. So I'm actually going to start with a little bit of homework first. So let's start with a small exercise. And this is especially relevant for like the junior researchers and sort of the students in the room. Let's start with a small exercise where what I want you to do, let's make it interactive. Pick your neighbor or whoever is next to you and give them a 2-minute or a short elevator pitch on what are you working on. Right? Pick your neighbor, start. Pick your neighbor, and if you don't have a neighbor, just like find a notebook and write down some key bullet points on what are you working on. And then we'll revisit this at the end of this talk, right? So write down what you have right now, and then we'll revisit at the end of this talk whether your story has gotten better your storytelling has gotten better and so on. Okay, 2 minutes. It's 10:06. Papers down at 10:08. Okay. I don't need to do this homework because I'm here on stage. Okay. All right. Pens, papers, voices down. So just sort of make a mental note of what you said, and your neighbor can hold you accountable for what you said. We will revisit this at the end of this exercise and see whether your pitch got better, worse, or whatever. Right? Okay. Cool. Thank you. Thanks for willing sort of participants in this exercise. So okay. So your elevator pitch is now set in stone. We will revisit at the end of this talk what your elevator pitch looks like. Okay. Okay, that's your first small exercise, and unfortunately, again, I'm known to do this. Your homework does not end now. Now we have a pop quiz. Okay, so here's a pop quiz for you. Here's like some 4 very famous people. So I'm a fan of trivia. So here's like for trivia lovers in the audience. Here's some 4 famous people. One of them is a famous Hungarian graph theorist, mathematician. One of them is the only person, as far as I know, to have won both a Turing Award and a Nobel Prize in economics. One of them was a DARPA program manager, and one of the people here is a very famous computer architect from the early eras of supercomputing. And if you've ever taken a computer systems class or an architecture class or a parallel computing class, you've probably heard of a law named after this person. Okay. Okay. Volunteers. You can also like take pictures and put it into images.google or whatever and find me the answer to. All my exams are open book, so I have no problem. So, any takers for who these are? Anyone know?
Von Neumann?
Sorry?
Von Neumann?
Von Neumann, I don't think he has a Turing Award. I don't think so. Or none of them is von Neumann, but good guess. If you had to pick a famous economist and a computer scientist, that's a good guess. Sorry? Erdos is a great answer, but no. Erdos is a great answer. Fits some of these things. I think he's Hungarian, mathematician, but not one of these people. Sorry? Sorry? Oh, Rubik's Cube. Oh, no, he's not. So, Moore. Moore's law, great guess, great architect, Intel person, not the law I'm looking for. Sorry? Amdahl's law. Which one is Amdahl? Okay, this is Jean Amdahl. Okay, thank you. Radhika gets like one piece of whatever. I owe you like a beer or a candy or whatever. Okay. One, Jean Amdahl. Okay, yes. Sorry? Herbert Simon. Which one is Herb Simon? This one. Okay, great. So Herb Simon happens to be from my alma mater and also where I work, Carnegie Mellon, one of the stalwarts of like AI and economics. He's the only person to have won both the Nobel Prize in economics and the Turing Award, by the way. So if one was hard, the guy got 2, right? So this is Jean Amdahl from the era of supercomputing, parallel computing, like Amdahl's law. Fantastic law, guiding principle for systems design. The other 2 are a little harder. Oh, so who said that? Oh, great. George Polya. This is George Polya. There's this beautiful little book called How to Solve It. If you've not read it, please go buy one. Or, I mean, I'm sure like there's also bootleg copies of it on like the internet. It's a tiny PDF. It's the best book ever. That is George Polya. This one's probably the hardest. The only people who might know this answer are the US academics who are actually writing grants to DARPA. If you ever written a DARPA grant, you probably know who this guy is. First one? Okay, I'll give you the answer. That's the hardest one. That's a person called George Heilmeyer of the Heilmeyer Catechism. So for those who don't know, so DARPA actually, the early days funded the internet, right? So DARPA funded many of the fundamental research programs, and George Heilmeyer, you can think of, he was the program manager at DARPA that funded a lot of these things. So you can think of like the early days of like, you can think of the DARPA program managers as the venture capitalists of the funding world, right? For research funding, they decide what gets funded. Okay. Now, why do I pick these sort of 4 random people, right? So okay, so we cracked the code on 3 of them: Heilmeyer, Amdahl, George Polya, and Herb Simon, right? So these are 4 extremely accomplished, eminent stalwarts in their field. The reason I'm actually picking them is they're actually the outline for my talk. So this is the outline for my talk, is I'm just going to use their wisdom. So like, have you heard this statement, like sort of like, good artists steal and great artists hide their sources, right? So nothing what I say is original, right? I'm just stealing from other people. I'm just distilling it into like a nice PowerPoint, and like that's all I'm doing. So there's no novel idea here. This is purely distilling the wisdom of other people who came before me. So I'm just going to say they gave this cheat sheet of this meta process for research. So George Heilmeyer basically tells you how to articulate your problem. Okay? Amdahl gives you this sort of this brilliant bit of nugget or insight on identifying the elephant in the room. What is the crux of the problem you're solving? Polya tells you how to solve it. And Herb Simon tells you, hey, why you should focus on the communication aspects of what you're working on. Okay? That's it. So this is the meta process for research. This is the one slide that you need. I'll get through each of them and why, right? So I'm just going to parrot the wisdom of other people, starting with Heilmeyer. So why is sort of the Heilmeyer interesting to me? Okay, and by the way, stop me, ask me, and again, this is just a model for the meta process for research. I'm sure there are other models for research as well. So first up is George Heilmeyer, right? So as I said, Heilmeyer used to be a program manager at DARPA, and his job, the sort of the best job in the world, is like he's sitting on a pot of money. People come and pitch to him, and he says, "I have to give you this money," right? He's like the venture capitalist of the funding world back in the day, and he basically realized that most people who come and ask him for funding or money have very bad ideas or very poor ways of articulating what they're working on. So he basically came up with this kind of like a checklist called the Heilmeyer Catechism or the Heilmeyer questions. And he basically said the following, right? Okay, you're going to come and pitch to me questions that you want, money. You're going to come and ask me for money. I don't have money, by the way. Okay, right? I'm an academic, so I don't have any money to give you, but I can at least give you the cheat sheet. Heilmeyer would ask everybody who came and pitched ideas to him the same set of questions. And he said, if you cannot answer these questions, there is no way I'm funding you. That's it, period, right? That's it. You have to answer these questions. And his questions were very simple. The first question he would ask is like, what are you trying to do? Which was the first question I asked you, right? It's like, okay, the exercise that you did was what are you working on, right? What are you trying to do? Articulate your objectives with absolutely no jargon. The less jargon you have of articulating what you're working on, the better it is for that sort of this elevator pitch. The second question he asked is like, how is it done today, right? If what you're working on is so important, presumably there is like a status quo, there's something that people are doing, and what are the limits of current practice? So second question. First question, what are you trying to do? How is it done today? What's the limits of current practice? Third question is like, what is new in your approach, right? Presumably you're pitching to get money from me, or you're working on trying to work on a SIGCOMM', NSDI, IMC paper. Presumably you have something new in your approach, which is why you're pitching that idea to me. And why do you think you will be successful, right? There's something new, there's probably something challenged. You have to say, why do you think you're going to be successful? The fourth question, and again, he put it number 4. I would actually contest why that is number 4. I would actually put at the top of the line. The fourth question was, who cares? If you are successful in your approach, what difference will it make to the world? Who is going to benefit from your work? Is it a network operator? Is it a programmer? Is it your user? Is it my mom? Whoever. Who's going to benefit from your work? And the last parts are more like sort of logistical questions about, hey, this is like project management. How much will it cost? What are the risks? How long will it take? What are the measures of success? And how will you check for milestones of your success? Okay? Now, this is beautiful, right? Now, actually, if you can answer these questions, you have an intro for your SIGCOMM paper next year. That's it. The first 4 questions are exactly the answers to your SIGCOMM paper. What are you working on? How is it done today? What are the limitations of prior work? What is new in your approach? Right? Why is it so hard that you actually have to solve it? Why it takes a smart person to solve this problem? Why do you think you'll be successful? Tell me the insight. And who's going to benefit? What are the measures of success? And show me like graphs or evaluations that you'll be successful. Right? That's it. So if you can answer these questions, you have a SIGCOMM paper. Right? That's it. It's not that hard. Okay, easy to say that. So that's Heilmeier questions, right? And this to me is actually surprisingly very hard to get right. So people start talking about what am I working on, right? I'm very excited to talk about what you're working on, but you sometimes forget who cares about your approach, what is the problem statement, what is new in your approach, what is the status quo. That's actually a template for articulating your goals of your problem statement. So this to me is the first step of any research before embarking on any research project is ask yourself the Heilmeier questions. And I'm guilty of this too, right? You get excited about doing stuff, and then you start talking about like jargon, you talk about, okay, BGP, NFV, SDA, and all this like jargon, you actually forget the crux of the issue of what you're actually trying to work on. And why it's interesting, why it is cool, why is it better than the state of the art. So for those of you who like collaborated with me or like, okay, have been students or in my group, you probably have seen some version of this. This is the repetitive part of me. I keep doing the same thing. Before you start anything, if you ever start a project, ask yourself the Heilmeier questions and write it down. Right? Write it down and periodically revisit, because as you do the research, your own knowledge of your questions, about your insights, about the prior work will change. It's okay to sort of pivot and change it, and pivot if the evidence suggests otherwise. Right? When you start, you believe that you have a key idea. As you try it, you have a hypothesis you're testing, the idea will change. You say, oh, this hypothesis was wrong. You come back and revisit your approach. Okay? All right. Now, one thing this doesn't tell you is how to actually pick the problems to work on. Right? So here's sort of my aside on how do you pick problems. At least when you talk to sort of senior people or other kinds of people, or like the people who go and give all these pitches and what they're working on, somehow it seems like they've had a vision all along, right? They give you this pitch as if like I've had this vision of like what I want to do all along. I've always wanted to solve like world hunger. I always wanted to solve like NFV or SDN or whatever, right? But it's tempting to think that this vision was there all along. But the reality, and you have to embrace it, is that the research process is inherently nonlinear and chaotic. There's like a lot of ups and downs, a lot of non-linearity, and it's much more bottom-up and jittery than many of us will care to admit, right? It seems like your advisor has this grand vision of what they're working on. The senior people in this room have this like grand vision, like, oh, I know what I'm working on, and I was always born with this wisdom. The answer is no. It's a lot of trial and error, and 90% of the time you're wrong. It's just we hide the parts where we are wrong, right? We're just very good at hiding when we are wrong and when we are stupid. That's all. So, and at least in my own sort of research, and it's useful, is more often than not, the provenance of research ideas really comes from 2 things. One is pain points. You talk to people who are in the real world, or your own research sometimes is the source of your own pain points. Hey, I was trying to do this thing. I was trying to collect this data. This data didn't exist. So I built a measurement tool to collect this data. I was trying to solve this problem. This tool didn't exist. I built that tool. That became a SIGCOMM paper. Right? I can tell you a story for every single one of my SIGCOMM papers or NSTI papers. It's either a pain point or a serendipitous conversation. That's it. And I can tell you the origin story of every one of those papers. So one is talk to people in the real world. You'll get the pain points from them, or your own researchers or your collaborators, talk to them. You get pain points from them. And the second part is all these like chance conversations in this community or hallways and stuff about, oh, you have these chance conversations that tell you about an interesting problem, an interesting data set, an interesting resource, or, oh, you have a hammer, they have a nail, or you have a nail, they have a hammer, right? Some sort of serendipitous conversations lead to very, very interesting research. And these two don't occur in a vacuum. You have to keep trying. You have to like believe in this process, keep trying, and then it will reinforce each other in the longer term. So in some sense, my idea for problem selection is like you will never ever find this like golden problem on day one. You got to embrace that I might start something small, keep looking for pain points and serendipitous opportunities, collaborate and sort of steal from the awesomeness of others. That's a great idea, right? You can always collaborate, and there are people who are much more awesome than you that you can benefit from, and you can build on look at the world, right? There's a whole ton of interesting problems in the world. Okay, so that's all about the first step, is the Heilmeier Catechism on how to pick a problem and how to articulate what you're working on. Any questions on Heilmeier so far? This is like part one. We're 25% done. Yes, question, please. Thank you. I hate listening to myself, but thank you for asking the question.
Hi, Noel from UCSB. So I was wondering, like, as a graduate student or like an early career researcher, it might be difficult actually to answer the more like logistical questions, like how much time will it take? How much will it cost? Do I have the skills, or does my group have the necessary skills in order to make a difference in that field? And so I was wondering if there's any, if you have any advice to be able to answer those questions.
Sure. First thing is like if you're a grad student, do not worry about cost. The cost is your advisor's problem. Okay. So first goal, right? I mean, your advisor is kind of like funding your work and is necessary for funding, but you should worry about whether you have a feasible solution, right? So this is where you have to pick something where you say, oh, look, what I need is like, I need a 10,000 GPU cluster before I can even get started. That's a non-starter for many academics, right? But that's also an opportunity, right? When you actually have a resource crunch of that nature, that to me is a reformulation of a problem where you say, I have to do this cheaper, faster, better than somebody who can throw money at this problem. So that is often, those things are also opportunities. But you're right, so you should pick. So these are more like for like project management and proposal stuff. So the risk you need to worry about, cost, probably not. But you do have to worry about like how long will it take and about the midterm things.
Yeah.
And the other part is also like, you have to divide that into like smaller problems. You might say, I have a grand problem, but then you work on a sub-problem that under some simplifying assumptions. And we'll get to that in the Polia section, where you might not solve the grand problem in one go. You might divide and conquer, break it into smaller chunks, make simplifying assumptions, and so on.
Yeah, so I'm really interested in that part, actually.
Okay,
How to break that great image into like smaller stuff.
Cool.
Thank you.
Great question, thank you. Any other questions? Okay, Marino, yes.
Yeah, Marino from Waikato. Do we have two different instances of this set of questions, one for grants and another for papers?
Good question. I think the last four are grant specific. I think the first four are grants or research. I think the first four are the same for both. Right? Yeah. And the good news about, I think grants need to be a little bit more grandiose and ambitious, whereas I think papers are much more scoped about like one sub-problem. Grants can be a collection of problems that lead to a grander vision. Yeah. Questions? Yeah, please. Thank you for asking questions.
So a follow-up on that question, like I often find it like a lot easier to answer like at least the first 4 questions in the context of one paper.
Yep.
But when I'm writing a grant and like you have to kind of collect multiple like little ideas together,
Yeah, yeah.
or like preparing like a talk on a broader scheme, like it's much harder to answer those questions. Any advice on how to go about doing that?
Good question. So grants is a different beast, right? I think, yeah. So I think, so grants are a slightly different beast. At least I can tell you my personal experience is actually, it's very, very hard for me to write a bottom-up grant where I have like 4 pieces and I'm stitching it together. It's easier for me to write like a top-down grant where I have a top-down vision of what I want to do, even if I don't have the slightest clue how to solve those problems. So I think to me, grants are more about the problem than about the solution, whereas a paper is more about the solution than about the problem. So at least for me personally, again, I don't think it always works, is for other people, it's like I write top-down grants, it's like, I want to solve this problem, I will make some arbitrary breakdown of sub-problems. That could be wrong, right? So they're not funded. Okay, I don't know if there are like NSF or DARPA people in this room. That's okay. To me, grants are not a contract. Grants are a funding or a promise of doing something. And oftentimes, as we go in the process, we will change it. So it's not a contractual obligation to work on, oh, I did thrust 1, thrust 2, thrust 3, thrust 4, right? Very rarely have I worked on thrust 1, thrust 2, thrust 3, thrust 4 when I do the research. Right? Something else happens, serendipitously, you find something, you repivot, you actually refactor it. But you have at least have a plan, but the plan is not a contract. Right? So I find it easier to write top-down with a plan, with the assumption that the plan will change. Yeah. And thankfully, the funders, like people like Darlene, have been nice enough to fund me, despite knowing that I don't have a plan. So. Okay, all right. Part 2, right? So now, presumably, you have a problem statement. You still don't know how to solve it. You don't know what's the sort of the actual way to solve it. Let's actually think about like step 2. Now you get to like Gene AMDAL. It's like, okay, what is AMDAL, right? And if you've ever taken like a computer systems class or an architecture class or a supercomputing class, you probably have heard of AMDAL's law. Very easy to state. It came from their world of like parallel computing and supercomputing. Is that the overall performance improvement gained by optimizing any single part of the system is limited by the fraction of time that part is actually used. Right? So imagine you have a program and you're trying to parallelize it. You can spend all of your effort in parallelizing something that only contributes 2% to the overall program, and you can make that 100% better, but your overall ROI is, return of investment is going to be limited. Right? This is not like a profound statement, it's an obvious statement. Right? So it's a very obvious statement, but an obvious statement that many of us always miss. So in a figure, basically, this is the AMDAL's law figure stolen from Wikipedia. On the x-axis, you have the number of processors in a parallel system. The y-axis is the speed up you get, and the different curves is the amount of parallelism that was possible to get out of it. Right? So if you have very little parallelism, even if you throw more processors at the problem, you're not going to get any benefit. Okay? Now, why is this important in the context of doing any systems research? Is every single time, at least for me, what happens is like you find some nugget or shiny object that you think you can optimize and solve, but what you can know how to solve may not necessarily be the thing you ought to be solving. So we go after the comfort zone of like where we know how to solve this problem, but that may not be the elephant in the room for actually solving the problem. So this is where things like measurement tools, profiling tools, data tools, talking to people to understand what is the biggest elephant in the room problem, right? So I could spend an incredible amount of time throwing all the GPUs and machine learning of the world to optimize some piece of the system, but if that some piece of the system is not the majority of my overall time, effort, wherever, right? Or like, imagine you're trying to even like go through traffic, right? You could optimize and go speed on a smallest piece of the road, but if that is only like 10% of your total time and you're being congested at some other highway, it's not going to benefit you. So the second part of this research process is really that once you've identified and said, okay, I know what problem I'm working on, really spend the time to understand what is the elephant in the room of that problem. Is the biggest pain point of that problem getting data? Is the biggest pain point of it finding which system to optimize? Is the biggest pain point network management? Is the biggest pain point verification? Could be very different things. So the second part of the problem is like once I know this is the rough space I want to work in, quickly zoom in and figure out some way, have a hypothesis on what is the elephant in the room problem. So that's the AMDAL's law applied to systems research in general, is if you don't know where your bottleneck is, if you don't know if you've not profiled your own system, you're not going to benefit from even if you can spend all your energy and your smarts in optimizing something, the overall benefit is going to be upper bounded. Okay. Not a profound thing, but I see this over and over again when I'm reviewing papers, when I work on problems, other people work on problems. You pick something that you know how to solve, as opposed to picking the thing that ought to be solved. Okay? Not a profound statement, but it's useful advice in general. Okay? So, step 1 is done. Step 1 is you picked a problem, you've articulated what problem you're trying to solve. Step 2, you've identified the elephant in the room. Step 3, this gets into like, how do I actually solve this problem, right? This is where I actually find this little book. This is like little genius of a book by Polya, and he talks, basically it's a book about like solving like geometry or algebraic problems for like, I think maybe high schoolers, but it's actually much more general than that. It's meta solution. It's a meta advice on how to solve any problem. And so he gives the thing about like, first you have to understand the problem. What are you asked to find? Find X. What is the value of this angle? Are these two angles equal? I mean, he uses like algebraic and geometric examples, but the same thing holds for a lot of our research problems as well. Can you restate the problem? Can you think of a picture to solve the problem? Is there enough information, right? Do you have the information to solve this problem? Are you using all the context, all the information that you have? Or do you need to ask a question to somebody and say, I don't have any information, maybe I need some extra hints from some other system? And then he basically talks about problem solving is not like rocket science. There are only a few standard meta heuristics to solve problems. And this is, again, from the book, is can you solve a general version of this problem? Can you solve a simple version of this problem? Have you seen this problem before? Have you seen a similar version of this problem in some other context? Can you break it down into, decompose and solve this problem? Can you break it down into smaller chunks where you make simplifying assumptions, solve it, and then revisit the simplifying assumption, right? But if you almost think most interesting research or most interesting papers will have this template, will follow one of these problem-solving strategies. So I put arrows on, like, my favorite ones is, can I solve a more general version of this problem? Have I seen a problem related in a different community or a different area somewhere else that is very similar to my problem? And I can give you like more examples of these if you have time, or you can ask me questions. And the other part for me, I'm a big fan of like whiteboarding. Can you draw a figure to explain the input and the output of a problem, and what is the measure of success? Most of the time, I cannot explain, okay, I'm trying to build this widget, okay? What is the input to a widget? I don't know. Okay, then you're stuck. You can't make progress. Can you just draw a picture of like how this thing that you're trying to solve fits in the bigger scheme of things, and so on. Then he says, carry out the plan. And the last part, which is actually very important for research, which often we miss, and I actually advise students to do this, you say, oh, I got a paper into SIGCOMM', or I submitted a paper to SIGCOMM'. That's not the end of it. That's actually the best time for you to sit down, revisit, review, and reflect and say, hey, could I have done this better? Could I have done it more efficiently? Could I take this and generalize it? Could I take it and extend it? Doing that sort of this post-mortem of reflection after you've done the work, after you've solved the problem, is actually very, very helpful. We often miss it because we are on a high, right? We have this like dopamine rush. We've gotten a SIGCOMM paper, or we've actually submitted a paper to SIGCOMM. The 2 weeks after your submission deadline is actually the best time to sit back without the deadline rush to actually think about, hey, could I have done this better? Could I have done this more generally? Can I take it and extend it to and think about other problems I can solve with it? I have a hammer. What are the other nails I have, and so on. So that's step number 3, right? Again, highly recommend this book. It's a meta book, and if you have kids, actually give the book to your kids as well, so catch them early. It's actually a very nice book about the meta art of problem solving, and it turns out there's not that many different strategies we humans use. There's the same set of things, is that some people are just more efficient at it than others. Any questions so far on Polya, Amdahl, and Heilmeier? This is useful? Okay. No questions? Okay. All right. And the last part is this thing. I mean, this is not really like sort of an action. It's not a concrete advice like Heilmeier, Amdahl, or Polya, but it's actually often very useful, especially for students who are actually thinking about like, how do I write papers? How do I give better talks? And to me, the words of like Herb Simon are actually super important. So back in the 1970s, this is where like the sort of the people of wisdom can see things coming far ahead of what we can see. So he actually made this bold statement in the 1970s that in the future, the scarcest resource is going to be human attention. So we're going to live in an information-rich world, and information as a resource, what it consumes, is the attention of its recipients. Right? I have all of you as a captive audience, so your attention is the scarcest resource. Right? And thankfully, SIGCOMM has given me this stage, and I have you as a captive audience. But that is the scarcest resource in the world. So if you're writing a paper, the scarcest resource is your reviewer's attention. If you're giving a talk, the scarcest resource is your audience in the room. And what we have is a wealth of information. Right? I can go right now. You can be on TikTok, you can be on YouTube, you can be checking your email, you can be checking Slack. We have an abundance of information, which means that it creates a poverty of attention. So he actually had this idea of like information sort of attention economics, that in the future, and we're already living that future, because he said this in 1970, that in the future, we're going to have a glut of information, and the attention of people is going to be the scarcest resource. Now, what does it mean for us is that we need to be really, really good about articulating what we are working when you write a paper, right? The writing part of it, the talk part of it is almost as important as doing the work itself. Because I don't know if you've thought about the PC process, right? I'll give you sort of the what actually happens at a PC meeting is like, I have to read 30 papers when I'm on a program committee. Chances are I've read your paper like 3 months before. When I come to the PC meeting, if I want to fight for your paper, I have to like page back the high order bits of your paper 3 months after I've read it and come and fight for you. So, right, you better write it well and tell me and spoon feed me as a reviewer how to fight for your paper. If you're like, I don't understand what is novel about your problem, I don't understand what is hard about your problem, if all I come to the PC meeting and says, they did something, they did a lot of engineering, they seem to have done a lot of work, you've lost the attention of the person championing you, and that person has lost the attention of the rest of the people in the committee. So make sure you actually write your problem statements, write your solution statements well enough that even though you have a memoryless, stateless process that's trying to fight for you, that process will actually fight for you. So that's why when you go read the papers, the public reviews, right? The reviews are written as soon as you write the paper, but the PC discussion, the PC meetings happen much later. So think about like the paper summary, whether the summary actually matches what the paper said, whether the contribution statements the reviewer said were actually matching what the paper said was the contribution statements, and you'll often find there are mismatches. Okay? So that's like the fourth part, right? So really spend time on the making sure your papers are good, really making sure your talks are good, because that's what people are going to remember. I think one meta bit of advice, I think Dina Papagiannaki, I don't know if many of you know her, she once told me, or I think she told this advice, is like, treat any talk you ever give as your job talk. So in faculty markets or research markets, you actually have a job talk. I have to come and give a talk. She said, like, treat every talk you ever give as a job talk, because somebody out there, somebody is looking, somebody out there is judging, and they're going to remember what you said. So treat every talk you ever give as a job talk. Make sure your talks actually stand out when you get an audience and a podium. Okay, that's basically my cheat sheet. Is use the Heilmeier Catechism for any new project, formulate and write a Heilmeier document for yourself. Use the Amdahl philosophy for any process, performance, or a bottleneck, profile the heck out of that, and identify the high order bits where your high order wins are going to come. Use the Polya framework to formulate the problem, refactor, visualize the problems in terms of the inputs and the outputs. And the last part, this is something I learned from my advisor, is he always said, like, you need to have empathy for your audience. You need to have an empathy for your audience attention, because they are being bombarded with all this other stuff. So you need to have an empathy for your audience. So think about that when you write a paper or give a talk and so on. Okay? All right. I still have time, so I will actually give you a very, very cheat sheet that I started using now for your sort of like problem formulation. So the animations are broken, don't worry about it. Okay, so here's you are trying to do your work. The first question you should ask yourself, and this is the cheat sheet you will see, is think about who is going to use your work, how will they benefit? So I'm building a tool for optimizing machine learning training. I'm building a tool for debugging networks. I'm building a tool for blah. So who's going to benefit? Is it an operator? Is it a data center operator? Is it like a video streaming provider? Somebody's going to benefit somewhere, right? Somebody. Who's that user persona is going to benefit from your work? Second question, your work, your widget, what is the input to your system? Is it data traffic? Is it a routing config? Is it a machine learning workload? Is it some algorithm? Is it code? What is the input to your system? Step number 3, what is the output? What are you producing? Am I giving a better algorithm? Am I producing code? Am I producing a static analysis? You should be able to say what is the input and output of your system. Then you have to very clearly define the measures of success. What are the metrics by which you're going to evaluate this piece of work? Oh, throughput, good put, latency, 99% latency, tail latency, time to debug. Pick your favorite metric, but write it down, because that's how you're going to evaluate your work. That's how the people viewing your work are going to evaluate your work as well. Number 5, once you define these things, now you get into say, okay, there's prior work. There is somebody else who has done this, prior work or extensions to prior work. Now you start talking about the status quo and their limitations. Now this is the silver bullet. You need to have some key insight. So you're a domain expert, right? Every one of you working on your problems are the domain expert that is trying to solve this problem. So you need to have like, I have a key insight. I believe this measurement can be better. I believe the system can be optimized in some way. I believe this code can be analyzed somewhat better. So there has to be a key insight that you have that you need to be able to articulate. This is my key insight. And this is the same for a paper. It's the same for a proposal, right? A proposal just happens to be an elevated or a higher level insight of why you believe this class of problems can be solved. And then finally, okay, this animation was broken, you finally say, here is my proposed approach or my key idea. This is it. This is my cheat sheet. Okay, sorry. This is it. You can I can send you the slides. If you start a project, ever trying to write a paper, trying to write a proposal, if you can answer these 7 questions, I think you're already on a good track. And I'm sure other people have better cheat sheets. This is my cheat sheet. Okay? And if you look at it, nothing here is original. 1, 4, and 5 are basically shamelessly stolen from Heilmeyer. Right? Why did I talk about Heilmeyer, Amdahl, Polya, and all of this stuff? Shamelessly stolen from Heilmeyer. Step 5, step 6, stolen from Amdahl. I have my insight on what is the key bottleneck. I have an insight on why the current work does not work. That is stolen from Amdahl. This input-output formulation, proposed approach, key insight, structure, shamelessly stolen from Polya. And the last part is from Herb Simon, is tell me who's going to benefit from your work, tell me, articulate clearly status quo, tell me clearly what is the proposed approach, right? So I said nothing here is original. These are like 4 great people who gave great advice. I'm just distilling it. Okay. All right, now's the second part of your homework. You did the original homework. You sort of set this stuff in stone. You had an initial checkpoint, right? There's a version 0 of what you're working on. Now, hopefully, try to use this cheat sheet and now try to give your elevator pitch again to your neighbor or to yourself. Okay? So take 2 minutes. It's 10:43. I believe you have 2 minutes left. Try to do the cheat sheet again. Okay? Use the cheat sheet. See whether your story got better. If not, I'll take the blame. That's okay.
Can I ask
Sorry?
Can I still ask something? Can I still ask something?
Oh, can you ask something? Oh, please. Oh, sorry. Yeah.
Okay, so I was wondering about the insights.
Mm-hmm.
So can you explain more what constitutes an insight? Maybe with examples.
Sure. Yeah, I think the insight is the hard part, right? I mean, that's the creative part of like research. So by the way, the students in the room, you have to do your homework, right? So we get to talk about questions. So you still have the homework to do about like revisiting your 2-minute thing. Insights, I mean, I can give a couple of examples, right? So I think, I'll pick 2 of my papers. That's the easiest to give, right? So one paper, we had this IMC paper on using like GANs for time series analysis. The insight there was like finding this analogy between all these people using like generative models for generating like cats and dogs and images and numbers and whatnot. And we're like, hey, I want to generate network traffic. It's the same as the other problem. It just so happens to be a different domain, right? Sometimes the insight is this analogy of seeing somebody else has solved this other problem. In other case, the insight is that you find a hammer somewhere else. So I give this example of universal monitoring, another SIGCOMM' paper that we wrote. I don't know if Alan's in the room. Okay, maybe he can simulate me. So even to the other talk, I think. So Alan's advisor had this paper called the Universal Sketch. You find this like insight and say that actually literally popped up in my Google Scholar feed. I'm like, dude, you have the best hammer for me. I have a nail on network monitoring. I've been struggling for a long time. Oh, this paper just sparked your thing is like, okay, that's the right hammer for my nail. That's the insight. In a lot of other cases, the insight comes from data-driven analysis, right? I really go through the logs and say, okay, that is the key problem. You have to troubleshoot and say, that is the key problem. That's the real problem there, right? Sometimes the data tells you the key insight. Okay, this is like heavy tail. Oh, this is like some caching behavior. Or this is where the tail latency is. So sometimes the insights comes from data. Sometimes the insight comes from random things that pop on your Google Scholar. Sometimes the insight comes from this aha moment of like random connections to other fields. I don't think there is a set answer there. If that was possible, then we don't need humans anymore. There is no creativity.
Can I have a follow-up?
Sure. Oh, actually, can I do a round robin?
Yes,
No, go ahead, Maria.
Okay.
So I understand the first part where it's like, why is it possible?
Mm-hmm.
And that's a nicer insight in that you can wait starting the work until you have this. But what about the cases where you are looking in the data for the insight, in which you can have the rest of the problem formulation, but you don't have this. So it's quite risky to start the project if you don't know if you'll have an insight.
This is, I think, okay, so this is This is also like other statement, I believe, like maybe this is like Winston Churchill or somebody else. It's like all great projects start from the willing suspension of disbelief. So if you want to do some cool work, you have to suspend your disbelief first, and this is true for all students, right? If you you say I have to beat the SIGCOMM paper, you have to believe you can beat the SIGCOMM paper. So you have to have the suspension of disbelief that you can beat it, and then you will beat it, right? So this is like, so you have to have that trust or the insight, and sometimes you may not have the confidence. I mean, you as a student, then you believe in the wisdom or the trust or the belief of your conviction of your advisor or your collaborator, who's actually worked in this problem space enough to know that there is a pony there. If not a unicorn, at least there is a pony there, right? So you got to believe that. So somewhere you have to suspend your disbelief. All creative stuff have to suspend disbelief. Yeah, thanks.
So, Vyas, maybe for the people who are starting in the room, the first question I have and then a comment is, the first 3 out of the 4, does the ordering matter?
In terms of this cheat sheet?
Well, the 4 things,
the four people
pieces that's presented, right? Like, I can imagine that those first 3, the ordering can change, or even you can go back and forth between them, I think.
Absolutely. So,
Fair
yeah,
statement?
great. No. So, thank you. Thanks for raising this, right? So, every time I give this, it's like, oh, it looks like this beautifully linear process. It is anything but linear. You have to keep going back and forth, right? You say, I did the Heilmeier thing, I found the bottleneck, my hypothesis of bottleneck was wrong, go back and reformulate. Okay, I found the bottleneck, I think I have a solution, I tried it, I'm banging my head, it's wrong, okay, go back and reformulate, right? So this is actually, there's an iterative reinforcement learning, refinement, active learning loop going on here that is not shown in this picture.
So thank you for that. And then if we go to the cheat sheet, I'll notice number 7. I don't know about others in the room, but this to me looks highly familiar because I think there was a point in my life where I recognized that doing number 7 first is actually the wrong thing.
Yes.
To do, but very common first
It's
thing.
very common mistake, right? It's like, yeah, you believe that you actually start from the solution and then you forget what problem you're actually trying to solve. It's like most of the time, my student is there, okay. Most of the time, like, somebody says, oh, I have this answer. I'm like, okay, this is the answer, what is the problem? Like, I'm explaining like I'm 5, like what problem are you trying to solve? I'm like really, really slow them down. And I said like, okay, sorry for slowing you down, but please tell me what problem you're trying to solve. Yeah. And this actually happens in like product, happens in engineering, happens in startup, happens everywhere. It's like people are excited about like I've solved the problem, but they forget what problem they're actually solving. Yes, you are up next.
Hey. So I'd like to come back to the aspect of getting funds and grants.
I don't have any money, by the way.
Yeah, like what could be your recommendation? Because I've got limited knowledge on grants, right? But I can imagine you need to fit your like problem space somehow to the funding framework. Is it part of requirement to that comes to your framework, or is it like side thing that you try to ignore and you know you need to fit somewhere to get the money for the research?
So again, funding is a very, very complex beast. And funding is different between US, EU, Australia, whichever country, whichever region you are in. And even within that region, there are different kinds of like funding vehicles. For example, the National Science Foundation, which I'm very grateful to, it has a much more like a bottom-up funding model where people propose stuff and then interesting stuff gets funded. DARPA is always top-down. They're like, we're going to build the internet, tell me a proposal. We're going to do self-driving car, give me your best ideas, right? So different, and even like NSF sometimes says, okay, we have a focused call, in which case it's a focused call on a particular subtopic of interest that somebody's decided to fund it, and then you see whether what your work is fits in there. So it really, really depends on the country, the funding vehicle, and so on. But I think irrespective of that, that sort of the Heilmeier catechism, I think, is universally true. Whether you are trying to go bottom-up, top-down, sort of scoped funding, you're trying to write a Google research grant, I think that process is the same, except the topic you pick might be slightly different. I don't know where you're from, but I'm happy to chat more. And the other part is like, the one thing about like, okay, similar to program committee meetings, you should also understand how like funding proposals work. Like being on a shadow PC or being on a funding panel is actually incredibly insightful. So, because then you realize that the people reviewing your proposal are not necessarily the experts in your field. They're experts in neighboring fields and they're trying to make a judgment on your work, which is where being able to articulate your idea, why it's new, why it's hard, why you are the right person to solve it is actually much more important. So, and many times in funding, also why you are the right person to solve it is as important as what you're solving, even though people say that that's not important.
Thanks.
Yeah. Darren.
One of my favorite meta approaches to forge a path through the chaos of research is turning bugs into features. So could you please tell us how this would fit into your framework?
Turning bugs into features, actually a great point, right? Talk about like how do you find problems, right? So when I talk about like the serendipity of like finding like sort of interesting sort of problems is often you look at the data and something looks anomalous and you're trying to explain it. I'm like, I can't explain this problem, right? And that's really the root cause of that leads to an interesting sub-problem, right? And you're like, I can't explain this performance. I can't explain this throughput. I can't explain these numbers. Like why, I think yesterday somebody was giving this talk about like broadband. Like why is the broadband penetration so low? Why is the bandwidth so low? Or I think you were talking about like tail latency. Why is the latency numbers don't match up, right? Why is this anomalies in your data, anomalies in your findings are often fantastic sources of doing like interesting research. Yeah.
Exactly.
So, and you need to turn those bugs. Or even this happens a lot in the software engineering program analysis world, is every time they have a bug, it actually leads to an interesting class of like software analysis, static analysis, dynamic analysis, and so on.
Yeah. Because you can either find the reason and fix it,
Yep.
or it's inherent, in which case it becomes a new problem.
Exactly.
And then you turn it into something interesting.
Exactly. Either way, it's a cool research proposal or a paper. You are up next. Yeah.
Thank you. I want to ask, sometimes we hold a hammer and find nails everywhere.
Yep.
And,
Nothing wrong with that.
In this workflow,
Yep.
actually a researcher focus on the nail and try to invent different hammers for the nail. So my question is, how do you balance, or which workflow do you think is right?
There is no right answer. I think it depends on what is most exciting to you. Sometimes you're excited by the nail. Sometimes you're excited by the hammer. In my own research, I can tell you which are the hammers, which are hammer-driven, which are nail-driven.
I think both are okay, right?
Yeah, both are okay, yeah. I mean, the easiest to motivate is actually a nail-driven thing, because then you've written your section 2 for your paper. The problem is well-defined. The hammer to nail is often harder, because then people might say, oh, that is the nail, I have a different hammer for you. I have a more efficient hammer. So the hammer to nail is actually a harder paper to write than the nail to hammer. Yeah.
Thank you.
That was pretty much my question.
Yeah.
Like one of ways, or one of the key insights for how Myers was between the why and how,
Yep.
right?
Yes.
So like students often emphasize the how and forget about the why.
Yep.
And so the question was kind of how much of a problem we have nowadays, maybe not so much at SIGCOMM', but like the overemphasis on the hammer, like blockchain, generative AI,
Sure.
you know, like and not so much on the nails. So like trying to fit this new thing that everyone is speaking about into different problems, and sometimes it doesn't work. And I like that.
And actually, sometimes that's actually useful too, right? Knowing why it didn't work is also interesting research, right? In the process of like going back to like, I think Daryl asked a question about a bug. You think this hammer is useful, then you realize it doesn't. And that's exactly how some of my work has happened, right? I thought like Jene was a cool hammer, and in the process of trying to solve it is like, actually, it doesn't solve my hammer. And then I have to go invent a new hammer. So that actually sometimes leads to better hammers too. Yeah.
Thank you.
Thanks. Xiaowei.
Yeah, hi. Yeah, Xiaowei Yang from Duke. Yeah.
Thanks for all the questions, by the way. No, thank you. Yes, I have your attention, so I've succeeded. So.
Very well articulated advice. Great, thank you. Yeah. I have a kind of like, either comment or question, right? So from my experience, there could be the cases that students did everything you put up here, right? It's like, there's like a lot of greater impacts for the potential work they could do. But then when it turns into paper, there's always this like intellectual part, not exciting enough, not hard enough that prevent the paper from, being published at a top venue. So I was just wondering what's your advice, to students on this type of thing, right? It's a great thing, if we did it, say we benefit a lot of people, but the academic wise, right? There's like this intellectual part, so the intellectual merit, right? So how to balance these two parts?
Great question. One I would say is like read other people's papers. So read Scott's papers. so I don't know, Scott is in the room, but I can paraphrase Scott. Sometimes Scott's papers are amazing. It's like, okay, there's nothing new in this work, but it's still worth doing, right? So and so I was like, there's not a technical piece of contribution in this work, but it's still worth doing, right? Or again, so I'm paraphrasing Scott here, but I'm just being flippant. But sometimes you have to say that the core here is actually the simplicity is actually valuable, right? So trying to contrive a complexity to something where the simplicity is the right answer. But then that becomes like a writing, how do you write it and how do you explain your core nugget or a core insight? It's like the core insight made the problem super simple, and then you probably have to emphasize the core insight better than artificially creating some complexity or, oh, this problem is NP hard or whatever, right? I mean, no, you don't need to do that. Again, but that means that you also have to get better at writing. A student has to get better at writing, but if you understood and internalized your own contribution well, you can write a very good paper. Yeah.
Thank you.
Sorry? That's bug to feature. Okay, yes. Last question. Okay, maybe one last question.
Yeah, thank you, Vyas, for very insightful, ideas. I had a question about, how would you take a SIGCOMM review and use that to improve upon your paper? Do you have any?
Great question. So, first of all, you have to see whether you agree with the review or not, right? Not all reviews were right. So, first of all, like when you see the public reviews, that's one of the reasons we're doing the public reviews and other things is like, not all reviews are right. But then you have to sort of read between the lines if you're a student and understand why was there a disconnect between what the reviewer thought and what you said. And more often than not, so if you think about, like I was telling somebody at the student dinner, right? You can think about reviewing as like a state machine going through 4 stages. The first is, I don't believe your problem is real, right? Second, I don't believe your solution is real. Or third, I don't believe your solution is hard enough. Fourth, I believe your problem is real, I believe your solution is real, I believe everything, you haven't evaluated enough, right? 90% of papers die at the first level. Most papers die at like section 2 or 3. It's like, I don't believe you have an interesting enough problem. So that means that then you as an author, as a student, have to really think about and work with your advisor or other people and say, or even sometimes, this is like seeing the forest for the trees. When you're actually doing the work, it's often very hard to step back and reflect and say, what is the other person thinking? So one thing that's very helpful is like give your paper to somebody else and have them give feedback to you. And this is why this process about like giving an elevator pitch is actually very helpful. Talk to somebody outside your area, talk to somebody who's not collaborating with you, and get their insight, because they will tell you like, hey, I don't think this is a real problem. I don't think this is a hard enough problem. I don't think a solution is new. I don't think a solution works. And then that kind of like articulation will actually help you the paper. You don't have to agree with everything the reviewer says, right? I mean, that's my thing. It's like sometimes I like, okay, that review was wrong, but then try to debug why the review was wrong. It's like maybe I wrote it badly. I didn't internalize my own contribution or the problem statement well enough. Yeah. I don't have a better answer than that. If I could figure that out, I'll have more SIGCOMM papers. So.
That's great advice.
Thank you. All right. Maybe happy to chat. We'll share the slides. Hopefully this was helpful. And thanks for your attention. Thank you.